So now what we're going to do is have a super oversimplified scenario. And this is the one that the book goes through, so it is what I will go through as well. We're going to talk only about potassium. So we know that there is a higher intracellular concentration of calcium than there is outside. So inside the cell, we have potassium ions at 150 millimolar, and outside the cell, at sort of rest, steady state, no net change, we'd have 5 millimolar. So we would expect this to lead to a flow of calcium out of the cell in terms of concentration or chemical gradient, right? That makes sense to us. Due to the resting membrane potential, where it's more negative on the inside, there is an electromotive force, this difference in potential, that wants to drive potassium in against its concentration gradient. So these two things are competing against each other. Okay? They might be working together. Maybe the signs go, depending on what you're moving and which way you're moving, maybe those things, you're going with your electrical gradient down your concentration gradient and it all is working well. In this case, these are opposing forces. Okay. An electrochemical gradient is a free energy gradient that arises from a combination of differences in electric potential and chemical potential across the membrane. Okay? That is our definition of this electrochemical gradient. And so what I'm about to get to and show is that in looking at sort of a free energy change for moving a potassium ion or mole of ions into or out of the cell, we're going to consider what is the electrical potential difference, what is the free energy change, the electric free energy change, what is the chemical or concentration dependent free energy change. And then we're going to sum those things together to get a total free energy change. Like I said, these two things are going to have opposite signs because we already know that based on looking at the scenario before we even start. So imagine a situation where no other channels exist except for the movement of ions of potassium. There's no leak channels. There's no other ions in play. We are only talking about potassium now. The movement of potassium is thus controlled by these two opposing forces. Okay. Pretend nothing else is involved. So then again, what we have here, we have an outward driving force for potassium ions to flow down their concentration gradient. And then we also have an inward driving force for potassium ions due to the electrical difference that exists at rest in a neuron. The resting membrane potential is the same as the equilibrium potential of potassium or the Nernst potential for potassium. I will write some equations down that hopefully clear that up. Okay. But basically, you can calculate what would be the equilibrium, the steady state, the no change potential for any given particular ion if I pretend that's the only thing that exists. Or say I want you to take into consideration potassium and sodium and chloride, but not potassium, whatever it might be. Remember that this negative 70 millivolts at rest actually encompasses a whole bunch of other stuff going on in and out of the cell. So now we're just talking about what would be the equilibrium for potassium only.